All right, this is section 7.2, which is called the disk method for volume. Sorry, you can't read the title here. But let's begin. The disk method. If we take a region in the plane and revolve it around an axis, which is usually the x-axis, we form a solid of revolution. So basically, I just take this little piece and I just spin it around the axis, making a solid. The simplest of these solids is a right circular cylinder or disk. The volume of such a disk is, remember, volume of a cylinder is pi r squared h. Well, r is the value of the function. H is however wide it is. So in this case, we call it pi r squared w because that's what it's labeled in this picture. To approximate the volume of a solid generated by any region, we can approximate the area using n disks. Each of my disks is delta x wide, and I just take that many disks and add them all up. And what do we know about using n of anything? We get closer and closer to the value as n approaches infinity. So the disk method, to find the volume of a solid of revolution with the disk method, we use one of these two formulas, depending on which axis we revolve around. If we have a horizontal axis of revolution, which is usually the x-axis, the volume is found by pi times the definite integral from a to b of r of x, which is just our equation, squared dx. Because remember, volume of a cylinder is pi r squared h. The r squared, that's r of x. The h is dx. It's our width. Vertical axis of revolution, so if I go around the y-axis or something like that, the volume is pi times the definite integral from c to d, r of y squared dy. It's basically just, instead I'm revolving this way, I'm looking at delta y. So let's do an example. Let's find the volume of the solid formed by revolving the region bounded by the graph of the square root of sine of x and the x-axis from 0 to pi about the x-axis. So that's a horizontal revolution. So our volume will be pi times the definite integral. Well, I want to go left to right, so I'm going 0 to pi. My function for my radius, well, the height of that is always square root of x, or square root of sine of x, squared, right, radius squared, times dx. All right, now I simplify first. Square root of sine of x squared is just sine of x dx. Now I evaluate my integral. Pi times the antiderivative of sine of x is negative cosine of x from 0 to pi. And then I have negative cosine of pi minus negative cosine of 0, which will give me negative negative 1, so positive 1, minus negative, so plus 1, which is 2 pi, which I would evaluate with my calculator, but I mean, 2 pi is a pretty straightforward one. 6.283. And there's our volume. So let's try another. We're going to revolve the region bounded by the graph of f of x and g of x about the line y equals 1. So this one gets a little weirder. I would personally draw myself a sketch. F of x is 2 minus x squared. So that's a parabola. It's upside down, and it's shifted 2 up. And that means square root of 2 is where we'll cross the y-axis, or the x-axis. There's my first function. My second function is g of x equals 1, which is right there. And I want the region bounded by that about the line y equals 1, which is that. All right, these little swirls are there to help me remember which way I'm rotating. So I'm rotating about a horizontal line. That's going to use a dx. my volume will be pi times the integral from left to right. Well, where does this equal 1? Might have to do a little work, right? Subtract my 2, divide by -1. All right, -1. Oops. X equals -1 and +1. Wow, all right, sorry. So we're going -1 to +1. Now our radius this time is a little different. For the radius, we only want this piece right here, which is just my function minus 1. So I'm going to take 2 minus x squared minus 1 squared dx. So if you're rotating about something that's not just the x-axis, you will have to subtract to get that space. So let's keep going here. Pi times -1 to 1 of -x squared plus 1 squared dx. And I will FOIL that out. I get x to the 4th power minus 2x squared plus 1 dx. And now I can find that definite integral. I have 1/5 x to the 5th power minus 2/3 x cubed plus x from -1 to 1. And that is pi times 1/5 minus 2/3 plus 1 minus -1/5 plus 2/3 minus 1. All right, I think this seems like a great time to bust out my calculator. So I have 1/5, can't see it, minus 2/3 plus 1 minus -1/5 plus 2/3 minus 1. And I'm going to multiply that by pi. My answer is 3.351, or I could have said 1.066 repeating as a fraction times pi. 3.351. All right, so then there's also a situation called the washer method. And if you think about a disc versus a washer, a disc is just, a solid one piece. A washer, though, has a hole in the middle. So the washer method is in order to find the volume of a solid with a hole in the middle. We're going to think of a washer instead of a disc. So basically we're saying, I've got some area, and I'm going to revolve around a line that isn't actually touching that area, which means there's going to be a gap in the middle. So the washer method, volume equals pi times the definite integral from a to b of capital R of x squared minus lowercase r of x squared dx. Capital R of x is the outer radius. That's the bigger one, always bigger. Lowercase r of x is the inner radius. That's what I call the hole. Please be careful. Make sure you square before subtracting, not subtract and then square. So let's try one. We're going to find the volume of the solid formed by revolving the region bounded by these two graphs about the x-axis. So we've already got a picture here. The first thing, though, is to figure out the bounds. I want to know, when does the square root of x equal x squared? Well, when x is 0 and when x is 1. No really simple way about that besides to use our logic here. So we're going from 0 to 1. So volume equals pi times 0 to 1. Now I need to know the outer area, or the outer function. I pretend it didn't have a hole in it, essentially. So the outer function here is whatever that one is. Well, I happen to know that's the square root of x, because x squared is this one. So the top function is square root of x squared minus the whole will be x squared. So x squared and then squared dx. So top, whole thing as if there was no gap, minus the thing that'll form the whole. And now we just follow our basic integration techniques. We have x minus x to the 4th power dx. So that's pi times 1/2 x squared minus 1/5 x to the 5th power from 0 to 1, which is 1/2 minus 1/5 minus 0. So 1/2 minus 1/5, and then times pi. We get a volume of 0.942. Let's find the volume of the solid formed by revolving the region bounded by y equals x. Now let's look at an application of this. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? So to do this problem, we need to think about what a sphere would be. To get a sphere, I could take my x and y axis. I could take a semicircle and revolve it. That would make a sphere. Then I need to cut a hole through the middle. So I want to cut it off like that. So I just have this piece that's getting revolved. So I would come up with, what's the equation of that half circle? Well, the radius is 5, centered at 0, 0. X squared plus y squared equals 5 squared. So y equals the square root of 25 minus x squared. That would be the semicircle. This slice that I'm making has a radius of 3, so that's just y equals 3. And I'm integrating from, really I just need to integrate from there to there, which would be when y is 3. So I'll do a little work. 3 equals the square root of 25 minus x squared. Square both sides. Negative 16 equals negative x squared. That's positive and negative 4. There we go. Now I can set up my integral. I need pi times the definite integral from negative 4 to 4 of my outer radius is the circle, which is square root of 25 minus x squared, minus my inner radius, which is 3 squared, dx. I could have done the same thing rotating about the y-axis. I could have rotated about a random line somewhere else on the graph if I wanted, but I just felt like the x-axis would be the easiest. That's where I drew my picture. So pi equals definite integral from negative 4 to 4 of 25 minus x squared minus 9 dx, which is 16 minus x squared. There we go. Now we take the antiderivative, 16x minus 1/3 x cubed from negative 4 to 4. And 16 times 4 is 64 minus 64 thirds minus negative 64 plus 64 thirds. Now I'm going to break out my calculator. 64 minus 64 thirds times pi gives me 268.083. And this one I have a label for cubic inches. Remember, volumes are cubic. We were working in inches. And there's one more thing we can do with these solids with known cross sections. So basically, I'm going to tell you, I know what the cross section looks like, you can find the volume. So if we know a formula for the area of an arbitrary cross section, so if I slice through that solid somewhere, and I know how to find that area, I can find the volume. Common cross sections that we'll talk about: squares, rectangles, triangles, semicircles, trapezoids. We already did circles because that was our revolution stuff. To find the volume of a solid with a known cross section, if your cross sections are perpendicular to the x-axis, so that means that's the line I know about, there's my cross section going up, the volume is the antiderivative from a to b of a of x dx, where a of x is the area of my cross-section. If cross-sections are taken perpendicular to the y-axis, we go antiderivative of c to d, a of y dy. So that means this way, that's my a of y, well, my area function of that cross-section. Let's look at what that means a little bit. This is a solid, all right? We got a little triangular situation here. The base of it is the region bounded by the lines 1 minus x over 2 and negative 1 plus x over 2, and x equals 0. The cross-sections perpendicular to the x-axis are equilateral triangles. All right, so we have, this is what the figure looks like. They also drew the flat xy coordinate plane version. Here is the cross-section. But up into the air, when I make it 3D, that's an equilateral triangle. So first thing we need is, how do I find the area of an equilateral triangle? Well, we know it's always 1/2 base times height. So it's going to be 1/2 times the base times the height happens to be in a special right triangle like this, the height is the square root of 3 times that base. But what is the base? Well, the base is f of x minus g of x. So the area of this triangle is 1/2 square root of 3 times f of x minus g of x squared. That's the area of one triangle. I need all of them, so I need the integral from 0 to 2 of this. So let's plug in some numbers here. 1/2 times the square root of 3 times f of x is 1 minus x over 2 minus g of x is negative 1 plus x over 2 squared dx. All right, I'm going to take this square root 3 over 2 out front. I have, combining like terms, I have 2 minus x squared dx. And I can multiply that out. 4 minus 4x plus x squared dx. And now we antiderive. Square root 3 over 2 times 4x minus 2x squared plus 1/3 x cubed from 0 to 2. All right, if I plug in 2, I get 8 minus 8 plus 8/3. And then if I plug in 0, I just get 0. So I really have 8/3 times square root 3 over 2. Type that in my calculator. And my volume is about 2.309. All right, now you'll have a worksheet to practice all this.